Hey, good morning, ladies and gentlemen. I'm Chris Bennett from PCSI, and I will be describing to you something about the magic of how this system works. You've heard from Kirk what the system is. You've heard from Vic where the resources come from to make it work. And it's my job to show something of the nitty-gritty of how it actually works. I'll be approaching this really as a bottom-up discussion. I'll be showing you, first of all, where the talk that I'm giving fits in within the overall system architecture that Kirk described. And then I will be showing you exactly how the bits and bytes get across the radio. Once you know that, we can start talking about how we do the various pieces that have to happen in order to provide the seamless service. How you control access to the channel, how you hop from channel to channel, how you move between cells, and so on. Once we have that piece of the system in place, I'll show how we do the end-to-end services, how we do the basic steps of the subscriber operation within the system. This is Kirk's network reference model. Obviously, I'm not going to go over it again in detail. The area that I'm going to be talking about is the area covering the radio operation, which is essentially the links between the MDG and the subscriber unit and between the MDBS and the subscriber unit. So in terms of the total network picture, it may appear to be only a small part of the operation, but it is the most critical part. The other thing to bear in mind is that what I describe here will also depend on a lot of activity that's happening in the background network. And so there will be all sorts of sleight of hand taking place in this region of the diagram, which I won't be going into in this talk. The objects that we're talking about across the air link are the subscriber unit, the MDBS, the MDG, and the channels between them. And within the protocol, we identify them with some internal identifiers, which Kirk essentially introduced earlier. There's a permanent identifier for the subscriber unit so that the network knows who it's talking about, and a temporary identifier which allows you to mask that permanent identifier from the outside world, and we'll discuss how that happens. The MDBS and the MDG each possess identifiers. These allow the subscriber unit to know where it is in the network and to know that things like a channel hop or a cell transfer have occurred. The connection between the two, the channel stream, possesses an identity which allows the subscriber unit to maintain continuity of service when there's a channel hop. And also for various special functions, particularly the multicast function and the broadcast function, their identities used across the air link. The multicast function, because this is essentially a closed user group and it must be distinguished from other closed user groups. The broadcast function is to distinguish one broadcast application, such as a weather report, from another, such as a traffic report. Obviously, broadcast is broadcast once you're within a cell, and so you don't need to distinguish broadcast zones, but you still need to distinguish who's going to interpret the message. These are internal identifiers. Externally, all the objects that you can address as a user of the system access points, which covers the applications, the data services, and so on, are addressed by publicly known identifiers, which follow the X121 format that Kirk described earlier. Within a standard ISO 7-layer model, the air-link protocols sit at the bottom 3 layers. The basic transmission, of course, is the physical layer. The control of the radio link is part of the link control that happens between the MDG and the MDBS. Mobility management is partly a network function, partly a link function, which is controlled by the MDG. And the control of connections, the flow of subscriber data, happens between the MDG rather, and the subscriber unit. The higher levels of protocol are something that we don't address. We keep the system open so that the application levels and the presentation levels and so on can be defined by the particular people who wish to use the network. So how do we provide the data transmission in this network? Vic laid down the fundamental requirements we had to meet as far as coexistence with the voice channel is concerned. The data service had to operate down to a carrier-to-noise level of 17 dB or better, this being the characterization that the voice cells have to meet. And this is sufficient to ensure that we don't interfere with the voice channels on the other cells if we meet the same envelope, and so on. We have to meet the same characteristics as speed fade characteristics as the voice cells, so we have to be able to support the service reliably over the same kind of speed range that you can find in a voice network. The protocol has to be flexible enough to support a wide range of applications, and this means anything from a small datagram to something that appears to be a continuous connection, which naturally led to a packet-type solution. The protocol had to overlay the existing voice network, and as Vic pointed out, it has to be able to get out of the way when there is a voice service. So it has primarily to be able to operate on non-dedicated channels. It must also be capable of operating on dedicated channels for carriers who wish to dedicate whole channels to the data service. To bring it up quickly, cheaply, get the market ready, we have to be compatible with the existing technology. No radical technological solutions which will take 10 years to implement. We have to be able to make the maximum use of existing parts, take advantage of existing cost curves, and so on. And the final result must allow full duplex access between multiple users on the reverse channel and a multiplex stream on the forward channel. So what we have in the system are two channels. We have the forward channel and the reverse channel. At an information level, the data on the forward channel appears as a set of frames, which are separated by frame delimiters or frags. And for this purpose, we just use HDLC conventions and the HDLC rules about zero insertion and bit stuffing. Very straightforward business. In order to achieve the error handling, the fade handling that we required, we chose to use a block coding scheme, and we chose to use a Reed-Solomon block code which chopped the source data stream into fixed-length blocks. Note that the divisions can happen anywhere within the source data stream. The frame can be of variable length. The frame can start anywhere in a block. It can end anywhere in a block. There's no necessary correlation between block boundaries and frame boundaries. As the forward channel has to be accessed by any number of subscriber units who are arriving at random times, the blocks are separated by a sync pattern to allow rapid acquisition on the forward channel. The transmission scheme that we used, consistent with the technology aims, we chose a Gaussian minimum shift keying modulation and a channel transmission rate of 19.2 kilobits per second. The reverse channel is somewhat similar, but not identical. On the reverse channel, you have one subscriber unit transmitting at a time, and between the transmissions, there'll be an idle period. The time when a single subscriber unit is transmitting is called a slot, and the succession of blocks that make up the slot is the transmission of the subscriber unit. At an information level, again, it's a series of frames which are delimited by HDLC flags. These again, are encoded into Reed-Solomon blocks, which again are transmitted using GMSK at 19.2 kilobits per second. The synchronization is somewhat different because the MDBS, which is listening to the subscriber units, only needs to, is dedicated to the channel. So it only really needs to synchronize at the beginning of the burst. And so there's a single pattern to allow for bit synchronization and block synchronization at the beginning of each burst. That's the fundamental transmission scheme. The access to the channel can happen in three ways. In other words, there are three different kinds of slots in the channel. The first mode is contention access. When there's a slot available, anybody who wants to transmit goes for it. They just try and transmit. And perhaps the strongest man wins, perhaps there's only one person transmitting, perhaps they collide. And if they collide, the system tells them to back off and to retry again. The second mode is a reserve slot. And the reserve slot is used if the system knows that a particular unit is supposed to transmit. For example, if there's an acknowledgement due at a higher level. And when there's a reserve slot, that unit and only that unit will attempt to transmit during the slot. Now, a system that's based purely on those two access modes tends to saturate with a fairly low throughput level when there are a large number of users appearing on the system. This is a well-known phenomenon which has been studied since the early days of packet data transmission at the University of Hawaii. So for these more heavily loaded channels, we have a third access mode called Demand Assignment Multiple Access, or DAMA access. And in that scheme, what happens is that a slot is declared to be a request slot. Each unit which wishes to make a transmission makes a very small transmission to say, I want to make a transmission. Once the central station knows who's transmitting, it then issues reservation slots to each of those transmissions in turn. As to the mechanics of how you announce what a slot is, what type of a slot, and where a slot starts, it works fairly simply. At a frame level, there is a particular type of control packet called the reverse channel status packet, or the RCS packet. And this packet announces what is the next type of slot in the system, whether it's going to be a contention, reserved, or DAMA request slot. It doesn't tell you when it's going to happen, it just says this is what it's going to be. The signaling of when it happens is based on the use of these sync patterns, and it essentially exploits a characteristic that you can have alternate values of a sync pattern and still maintain the synchronization correlation requirements. When a subscriber unit is transmitting, the sync pattern has the busy value to indicate that the channel can't be accessed by another subscriber unit. When the subscriber unit ceases to transmit, the MDBS detects this, and the next sync pattern sent is an idle sync pattern, indicating the channel's idle, of course. At a fixed time following that, the units which wish to transmit start their transmission. So you'll notice that the signaling of the availability of the channel happens without affecting the operation of the data stream at the higher level. You don't need to interrupt a frame or anything to send a special packet to do that. You get continuity of transmission. But your idle time is guaranteed to be less than one block. If we had a dedicated data channel, that would be all we would need to manage the resource within a single cell. But of course, we don't have dedicated data channels. Nor do we have a control channel which allows us to tell everybody where the next channel is going to be. So how do we control channel hopping in a way that is seamless to the subscriber? The fundamental resource is based on, could I have the slide back, please? Okay. fundamental resource, no, that slide, yes, thank you. Back. The slide labeled channel hopping protocol, thank you. Fundamental resource is based on the transmission of a list of free channels, so that at any given time the subscriber unit knows where the MDBS is expecting to find the next free channel for CDPD use. Now, a hop can occur for two reasons. The first is that you detect that the voice has come on board, and you just have to go there. If the MDBS fails to anticipate a voice usage, you just go. There's nothing else you can do. But most of the time, you try and predict where the next available voice channel is going to be. You have a fixed time on the channel for reasons that Vic described, and at the end of the time, you go to the most preferred channel on the list, and you indicate this is going to happen by sending a special packet, the switch channel command. The MDBS, when it switches, it just goes and it maintains the logical identity, the logical continuity of the channel stream, so that the subscriber knows that it's just picking up where it left off if it succeeds in following the switch. If the subscriber unit finds the switch channel command, then it just jumps. It goes to wherever the MDBS says it is, verifies that it's the same logical place, and carries on operating. If the subscriber unit fails to see the switch channel command, it starts searching for the channel by looking at the list of free channels. And by and large, that's where it should be able to find where the channel was that it was to jump to. Another aspect of the radio resource management is to ensure that we're maintaining proper power control in the system, that we aren't generating too much power to interfere with the voice or with other data users. And this is based on a feedback loop, which is controlled by transmission of a quantity called the power product. The subscriber unit measures the received signal strength of the signal it's seeing from its controlling MDBS. It then calculates the transmitted power by dividing the value it has for the power product in that cell by the received signal strength. And it then quantifies it to within the power steps that it has. Normally this should be sufficient, but an override ability exists if the subscriber unit finds that it's transmitting and it's not being heard. It can add a boost of 8 dB to its transmission power if needed. Similarly, the MDBS can tell somebody to back off if he's being overwhelmed by too much power from the subscriber unit. So that completes the basic system management within a single cell. The subscriber units will often be mobile. They'll be moving from cell to cell within a single system and from cell to cell between systems. The management principles that we use to control this in a seamless way are similar to what we did for channel hopping. The MDG finds out from its MDBSs and from its neighboring MDGs what are the channels that are being used for CDPD in adjacent cells. And it tells the MDBS of this information. The MDBS broadcasts this information, and the subscriber unit keeps a database of what are the adjacent cell channels that it can hop to. A transfer may happen for two reasons. It may happen because the MDG tells the subscriber unit to go to another cell. For example, this may happen because the MDG determines that the load in a particular cell is too high, and it may be better served in another cell which the subscriber unit can hear. More normally, a subscriber unit will initiate a channel acquisition on its own account because the signal strength from the MDBS has got too low. The subscriber unit goes through a channel reacquisition process which uses this initial list as a prioritization. Once it reacquires a channel, it detects the MDBS ID, which has always been broadcast on that channel, to know whether a cell transfer has occurred or whether it's just hopped to another channel within the same cell. If a cell transfer has occurred, subscriber unit tells the MDBS, hey, I'm here. so that the system knows the subscriber unit is moved. It re-registers. And then the MDG does some sleight of hand behind the scenes to recover the state of the subscriber unit's connections and also to clear out that information from the old serving cell. I'll have a few words on how system security operates, although I won't go into too much detail. There are several goals that we're trying to reach with system security across the airlink. We're trying to preserve the confidentiality of the user identity so that an eavesdropper can't really do any traffic analysis. We're trying to preserve the control of the system so that the subscriber unit can't be spoofed by a false MDBS. We're trying to validate that the subscriber is who he says he is and to allow the subscriber unit to know that he's talking to the network he thinks he is. The confidentiality is protected by a scheme of temporary subscriber IDs, which, as Kirk said, are changed at regular intervals. The system signaling is encrypted as far as possible. The encryption is sufficient to protect you against eavesdropping and to protect against any real-time spoofing of the system. Subscriber unit must always authenticate itself when it registers. It must also be prepared to authenticate itself on demand via an exchange of digital signatures. The MDBS will also authenticate itself to the subscriber unit on subscriber unit registration by a similar exchange. There's a couple of fallback measures in the system: clone detection and simply recovery from losing track of the chain of TSIs. Subscriber unit identity, the permanent identity, can be found by network inquiry. And also the network has the ability to tell the subscriber unit, go away, I'm simply not going to listen to you. So these are the tools that we have in place to transfer packets. I'm now going to describe to you how we control that transfer. And there are several levels of control. It really depends on the type of packet that is being transmitted. Certain packets which are broadcast packets which are multicast, certain control signals, are transmitted one time without acknowledgement. If you hear them, well and good. If you don't, presumably they're going to be retransmitted again if you really care about them at a higher level. Certain other packets which essentially are performing functions which are out of band, out of sync with the main data flow, and particularly this is the registration sequence, and certain other packets related to radio control, are acknowledged, but they're acknowledged on a packet type basis so that you can only have one packet of that particular type outstanding. But by and large, packet transmission is subject to an HDLC-like windowed flow control. It's not the same as HDLC, but the principles will be familiar to anyone who knows HDLC or X25 LATD. The endpoints for this windowing protocol are the subscriber unit and the MDG, not the MDBS. Each packet in each direction which is subject to this control is given a sequence number which is 5 bits inside. And in order to reduce the network overhead, we try and piggyback acknowledgements where possible. You don't have to acknowledge every packet. An acknowledgement quotes a sequence number which acknowledges all the packets before the sequence number named in the acknowledgement. So far, so standard. Where we have added some additional spin is in use of negative acknowledgements. This is to cut down on unnecessary retransmission across the air link. Packets which are received out of order, which essentially means that one of the earlier packets got lost for some reason, are stored by the receiver, be it the subscriber unit or the MDG. And the subscriber unit will send what's called a negative acknowledgement. The negative acknowledgement says, this is the packet that I'm expecting, and this is a packet that closes a gap that I'm seeing. Please transmit the packets in between. When when a packet transmitter receives one of these negative acknowledgements, it retransmits the packets which are covered in the negative acknowledgement. Also, if you don't receive an acknowledgement within a timeout, you will retransmit the last packet that you sent, hopefully either getting a positive acknowledgement or a negative acknowledgement. The second thing we've done with retransmission is we've offloaded the retransmission function from the MDG into the MDBS so that retransmission is contained within a cell. This protocol allows the sequence numbers to be transferred as you move from cell to cell, the result being that the flow of data is invisible to cell transfer, or rather cell transfer is invisible to the flow of data. But in certain circumstances, the two sides may get out of step, in which case we have reset and recovery procedures, again similar to those in Lab B. We also have a flow control based on receiver ready, receive not ready schemes, which will be familiar to anyone who's used those protocols. To give you some idea of how the retransmission protocol works, in this slide, which I'm sure the details of the numbers are a little hard to read, but in retransmissions from the MDBS, from the MDG, if a packet is transmitted to the MDBS and the first transmission fails, then the MDBS will time out at some later time and retransmit the packet. On the negative acknowledgement side, if a sequence of packets comes from the subscriber unit and one of those packets is lost, that gap is immediately visible to the MDG because it sees the sequence number, in this case 1, 2, 4. The MDG sends a negative acknowledgement saying, hey, I'm expecting packet 3. The next packet I saw was packet 4. This goes to the subscriber unit, which by this time has already transmitted packet 5. The subscriber unit retransmits packet 3. It knows it doesn't have to retransmit packet 4. It transmits the next packet in sequence, which is packet 6. And the MDG, which is happy now, sends an acknowledgement saying the next packet I'm seeing is packet 7. So that shows how the basic flow of data is performed within the system. I'm now going to move to a different viewpoint on how the system protocols operate. I'm going to look more at how the subscriber unit has to do various functions within the system. The first and most basic function of this, of course, is that the subscriber unit has to acquire the system, has to acquire the signal. As we've noted before, there is no dedicated control channel. The subscriber unit potentially has to search through several hundred channels in order to find a CDPD system. What can we do to minimize the amount of time that this is going to take? Well, we use a similar principle to what we did for channel hopping and cell transfer. The subscriber unit keeps a history of the recent channels that it was using. The theory being that more often than not, when you power up in a cell, the chances are quite good that you were recently using that cell, and so the channels that were used may well be the same. It's a good place to start. So you start by scanning those channels. And if you happen to find a channel, whether or not it's being used for CDPD or for voice, you can then make a guess that the most likely channels are the channels which are in multiples of 21 from the channel that you found, because of the basic structure of cellular, which was outlined earlier by the talk from Pactel. So we take these steps to minimize the channel search time, and we also have faster tuning inside the subscriber unit than might otherwise be required. Once you've found a CDPD channel, the process of locking on is fairly straightforward. You look for a forward channel sync pattern to confirm it's CDPD. You wait for a reverse channel status packet, which is announcing a contention slot, and then you register with the system in that slot or in the following one if there is contention. The registration process is required every time you power on and every time you do a cell transfer. It's used to validate that the subscriber's access rights to determine what he can do. It's used to notify the network of the current location, so that you can route calls to him, you can route multicast messages to him, and so forth. And it also causes assignment of the temporary subscriber ID, which will be used during the course of the subscriber's lifetime on the network. While you're doing the registration, it causes the other activity, any other activity that might be in progress, to be suspended. This should be very brief, but, and it should happen seamlessly to the application process. But as far as the network is concerned, there's no point in continuing a connection if you're not sure who this guy is. When the subscriber unit is ready to power down, it will deregister from the system, and it will also, if the system doesn't see any activity from the subscriber unit for a sufficiently long period of time, it will deregister him from its databases. The registration protocol is fairly straightforward. The subscriber unit sends a packet called the registration packet to the MDG, which acknowledges it using the identity which the subscriber unit quoted in the registration packet. The network then does some sleight of hand to work out whether the subscriber unit is who he says he is and whether he's acceptable. Assuming he's acceptable, the network will then, the MDG will then issue him with a new identifier. And this is acknowledged by the subscriber unit. To preserve security, the actual change of identifier does not take place until this handshake is completed. And once that's done, then CDPD traffic can begin or resume. The deregistration protocol, the power down protocol, is again very simple. The subscriber unit just sends out a deregistration packet and receives a response. Protocol supports all the connection and connectionless services that are required. The protocol can support up to 16 active connections for each subscriber unit, and these connections are separately identified within the overall data flow. The connections can be originated by the subscriber unit, or they can be terminated at the subscriber unit when they're being set up. So a subscriber unit can be called by a data service or by another subscriber unit. As well as the flow control on the overall data flow, there is separate flow control on the individual connections, so that, for example, one slow application process doesn't cause all the application processes to be slowed down. And this is again done using an RNR type scheme, which is tied to an individual connection. The network provides some facilities for enhanced security and for improved efficiency. There's some encryption, which can be selected at connection setup time to provide protection against eavesdropping of an individual connection and real-time decoding of that connection. You can also compress the data using V42 BIS type and other schemes to improve better data efficiency. These are selectable at call setup time, and they can be different between different connections. The network also supports an emergency level of service for people like earthquake, hospital, fire, that kind of thing, which receives an expedited level of treatment. If you're authorized for this kind of service, you can select that at connection setup time. The call setup protocol is based on an exchange of call setup and confirm packets. In each direction, there is a separate virtual circuit identifier, and the actual connection consists of the pairing of the two identifiers. So the call setup says, this is the identifier I'm going to associate with data flowing in this direction. The call confirm says, okay, for that particular identifier, this is the associated identifier for data flowing in the reverse direction. And then data segments going in either way quote the appropriate identifier. And a similar procedure happens if the call is set up by the network instead of by the subscriber unit. When a call is closed, each of the virtual circuits are closed by a call clear packet, and each call clear packet quotes the circuit number of the circuit that it's closing. The call clear packet can be, the closure can be initiated by either party. Doesn't matter who set up the connection. And in fact, the two parties can choose to close the connection simultaneously by an exchange of call clear packets. The other sets of services that are supported within the system are connectionless services. As we discussed, there are two classes of connectionless service. There's the so-called unreliable service, which is the classic datagram. It's a one-shot transmission, and any retransmission, any reliability is assumed to be the responsibility of the application for using that service. The network also provides a, quotes, reliable connectionless service. This is somewhat analogous to the X25 Fast Select. It's a single packet which is not associated with a connection, and its transmission is guaranteed across the air link using the windowing schemes that we've discussed earlier. For the point-to-point connectionless services, you can use either scheme depending on your application. For multicast services and for zone broadcast transmissions, they're inherently the one-shot or unreliable service. It's assumed that the application will be repeating the information if necessary. By and large, connectionless messages are not encrypted, but by the network, that is. There's nothing to stop the application service from applying its own encryption. But multicast datagrams, which are inherently supporting a closed user group, are given a level of protection by the network using keys associated with each multicast group, which are distributed to each member of the group beforehand. So in summary, these are the major features of the protocol architecture on the Airlink. We provide a full duplex shared wireless access using GMSK modulation at 19.2 kilobits, exploiting the bandwidth which is unused by the analog cellular traffic, or a dedicated channel if you wish to do so. We provided a contention and reserve channel access scheme, but there's an additional level of access control, of access management, which allows you to be adaptive to increased system load. The service is sustained seamlessly under channel hopping and cell transfer. It supports both the connectionless and the connection-oriented mode of services that are required with all addressing modes, point-to-point, multicast, and broadcast. And we provide levels of security and confidentiality and authentication and other features such as data compression. And that's what I have to say about the protocol. The next speaker will be Mike Lubin, who is also from PCSI.
Thank you, Chris. Those of us fortunate enough to have participated in the creation of the VSAT and mobile satellite industries in the 1980s learned several profound lessons in marketing to the mobile industry. We learned, number one, that service costs and subscriber unit costs were extremely important with respect to penetration of those markets. In fact, we learned that if you had a subscriber unit that was in the low thousands of dollars and a service that was in the low hundreds of dollars, you might in fact only penetrate 5% of the addressable market. But on the other hand, if you had subscriber units that were in the $500 range and services that were in the $50 per month range, you might approach 50% of the addressable market. The second thing we learned is that the user community wanted ubiquity. They wanted services that were everywhere, and in some sense, they wanted the democratization of information distribution. They also wanted that ubiquity taken indoors, and they wanted to make sure that these services reliably penetrated buildings. We also learned that the traditional mobile community would become a personal community. And in fact, that meant that the units had to become small, compact, and low cost. And finally, we learned that the industry was in fact fed up with well-intentioned but unfulfilled promises of great services using exotic technologies with subscriber unit costs that in fact were not achieved. With those lessons in mind, we and our colleagues decided that, in the words of Woody Allen, showing up is 85%. And therefore, the approach chosen was an approach that would permit the industry to quickly put applications, subscriber units, and services to the customers as quickly as possible. In fact, the approach chosen was an implementation which minimized radio costs, radio sizes, power consumption through the extensive use of off-the-shelf radios, components, and technologies. And in fact, to make sure that the industry became a great success, the creation of the approach was to provide designers with tremendous flexibility in the kinds of products and services that could be provided to the ultimate customer. It is believed that the market will in fact be segmented with respect to subscriber units based on features and pricing of units. We envision subscriber units that might contain only CD/PD packet-only services. This will obviously be the lowest cost subscriber unit and can be implemented with either very powerful processors or with very low-cost VLSI technologies. In fact, however, the uniqueness of the system that is being described today is that it can not only provide packet messaging, but it can give, with the same technology, users access to AMP's cellular telephony. And we therefore believe that there will be subscriber unit products that combine packet messaging with cellular telephony. As you know, since we are using the cellular network, it is also possible to offer cellular circuit switch data above and beyond the above presented features. And finally, many of the PC user communities are very interested in new high-speed and low-speed voice modem and fax cards that are going to become ubiquitous. And we believe that these high-speed and low-speed telco interfaces will also become options that will be associated with these various subscriber units. We therefore believe that the standard which is being discussed today, or the approach being discussed today, will provide subscriber unit manufacturers with tremendous flexibility with respect to the kinds of subscriber units presented, the kinds of features, and the kinds of costs that a variety of consumers wish. We envision products that may actually have a twofold difference in their eventual cost to the consumer, depending upon which feature set is in fact selected by the manufacturer. With respect to performance, we believe that subscriber unit manufacturers will choose either implementations in powerful DSPs and CPUs for the digital baseband processing, or some of them will choose to develop very compact, low-power consuming custom LSI. One of the great successes of this approach is that it can work with very modestly modified off-the-shelf cellular radios that can be found at 0.6 watts or 1.2 watts, or in fact, because of the packet nature of the approach for packet data, certainly one could go to a 3-watt unit. We believe that manufacturers will differentiate their products through differences in performance due to antenna diversity. We know that there are multiple forms of antenna diversity: spatial diversity, polarization diversity, field diversity. We also know that there are different kinds of combining and switching schemes, each of which has a unique place in the market with unique performance characteristics. We believe that manufacturers will have internal and/or external antennas, depending upon the subscriber base that they wish to address. And in fact, depending on pricing, some subscriber unit manufacturers will decide to give their products performance edge by using radio components that will provide improvements above and beyond current technology. One vision of the products that will be developed is products that are integrated into existing PCs, pocket organizers, and data terminal equipment. We also believe that these units can be made standalone and external, either as slices to individual data terminal equipment or as complete standalone units. We are all aware that the industry is getting behind the so-called PCM-CIA Revision 2 form factor. It is certainly within the possibility of this technology that it can be implemented in PCM-CIA Revision 2 form factors with respect to all of the digital processing. And in fact, it is very likely that the entire radio modem, perhaps without battery, can be packaged in PCM-CIA revision 3 form factor. We believe that some manufacturers will choose to make this device look exactly like a cellular telephone with the enhanced performance possible through the CD-PD protocol. We also believe that those manufacturers who use powerful 30 MIP DSPs and powerful CPUs for implementing V32 and V42 for their high-speed telco interfaces will choose to implement various protocols in those processors that will support CD-PD and also very advanced cellular features associated with hands-free technologies, specifically acoustic echo cancellation, noise reduction, voice activation for getting longer battery life, and voice commands itself. And because all of us want this to be a successful launch and realizing the schedules that are desired for safe introduction of this new standard or new approach, one wishes software downloadability to permit changes, revisions, and improvements. When one realizes that in a cellular telephone today, approximately half of the weight is due to the battery pack, obviously one wishes to do everything possible to preserve power. The current approach has a sleep mode that will permit battery saving with a duty cycle that has not yet been determined as the final, but will be tested in field tests. The new unit, as it was discussed before, the new approach, has a very flexible adaptive power control, which should benefit in power conservation. And finally, with the evolution of technologies for PCs and palm tops, etc., heading towards 3-volt technology, it appears that the entire digital processing for this approach can be accommodated in the 1993 timeframe with 3-volt technology other than the RF components. And that, of course, would provide quite a bit of flexibility for the designers as to how they want to take advantage of that possibility. Most importantly, the CD-PD approach permits, I believe, for the first time, the integration of cellular voice, wireless circuit and packet switch communications with high-speed telephony, modem, and fax and compression in a single package, and in a single package that can actually be extremely compact. The conclusion is that an approach has been selected where basic radio modem unit costs can be provided comparable to analog cellular phones with significant differentiation among subscriber unit manufacturers due to the inclusion or exclusion of a variety of features. The importance here, however, is that we can begin talking about subscriber units with costs comparable to cellular telephones. We also believe that the approach presented here today permits subscriber unit development times and costs for the world manufacturing community, which are quite short and quite modest by comparisons to other techniques and other components. There was no desire here to use extremely exotic technologies which might provide some epsilon improvements, but in fact would delay introduction or make the implementation of the subscriber units very costly. And lastly, based on my introductory comment concerning the sensitivity of the market to the size and the cost of the subscriber unit, an approach has been chosen whereby subscriber unit sizes and costs can truly uniquely open mass consumer markets and address Lee's comment about 13 million subscribers by the year 2000. So in summary, an approach has been chosen which I believe can revolutionize voice and data communications on an existing infrastructure which has been implemented over the last several years. With that, I would like to introduce Mike Roman, who is the manager of network product marketing at IBM Information Networks. Mike comes to us with 22 years of experience at IBM via Notre Dame, University of Pennsylvania, and Wharton.
Thank you, Mike. Well, by now you've had a chance to see an awful lot about the CD-PD system, and I'll tell you it's a great pleasure for me to be part of the agenda this morning and to have been part of the efforts in the last few months to help create this initiative. My objective here is very simple today. What I'd like to do is simply describe the components and the connectivity of the CDPD field trial to customer applications on the information network. Now, you're going to hear from Mark Taylor a little while from now, and he'll explain to you the nature of the field trial in a little bit more detail, but you know at the announcement a few weeks ago that a field trial for this summer was part of the announcement. And in that announcement, of course, Sears as well as the IBM Information Network will participate. So the first purpose here is just to describe that transport flow, that networking capability. Second of all, to describe the network connectivity beyond the field trial that will be used by other value-added networks and customer networks and applications. This first chart describes then the field trial implementation. Our objective is to attain full end-to-end communications, and it will be accomplished with the following components. Application software that will be running in a mobile PC and that has a corresponding host-based application that the PC user wishes to access. The SU and some of these other components, of course, you've heard about from Kirk and from Chris, but I'll just mention them briefly in relation to what they do in this transport path. The subscriber unit is will be a mobile PC equipped with a Cellular Plan 2 modem, for instance, a PC radio with the appropriate modem, either integrated or external. Of course, for the field trial, it will only be an external modem. The subscriber unit through the Cellular Plan 2 modem communicates with the data over cellular network via the AirLink protocol. The MDBS is the mobile data base station which resides in the cell site and communicates with the SU via the AirLink protocol. The MDBS makes the initial transition between the AirLink protocol and landline communication systems and protocols. The MDG is the mobile data gateway for the CDPD system. It manages the radio resource, as Chris just explained, for the cell sites for which it is responsible, and performs services in the data over cellular networks such as landline bandwidth management, connection management, authentication, and some of the other points that Chris made. The NIM is the key component that we want to focus on here. The Network Interface Manager is the bridge between the CDPD environment and a value-added network such as IIN. The NIM does address reconciliation and routing into the data network and, if necessary, protocol conversion. The next component, the dial gateway, is a standard interface into IIN for dial applications that was just very appropriate to use for this particular requirement. The software that was developed for the NIM is quite closely coupled with that gateway. In fact, they run in the same hardened PS2. And then, of course, is the information network and the application host processor and customer software. Our field trial objectives are very simple. Our intent for the field trial is to be able to display end-to-end communications for standard interactive applications such as sales support, order entry, electronic mail, other office-type applications, or database inquiry. Let me focus now on the NIM, which I said is the key component for this discussion. During the field trial, the NIM will provide several things. Address conversion from the CDPD network to SNA in this case. The application software running in the SU will actually create an asynchronous data stream that will be passed to the Cellular Plan 2 modem. The subscriber unit will packetize the data and add headers that identify the source. The information is then sent through the CDPD network to the NIM where the data is depacketized and the address translated, in this case, to an SNA LU name. After the NIM unwraps the CDPD routing headers from the packet, it routes the data that originates in that application on the PC to the correct corresponding host-based application. The NIM also acts as a protocol bridge, in this case converting an asynchronous data stream into a full-screen data stream that in effect is what the host application will see. In addition to that full-screen conversion from asynchronous to 3270 data stream, data compression and encryption and a threefold modem speed performance enhancement will be provided in this environment. Finally, there's a limited set of operations, maintenance, administration, and provisioning functions that are provided. Examples of these functions are measurements, such as the number of packets received and the number of packets transmitted to and from the CDPD, as well as to and from IIN. Error logging to record any event that affects the operation of the NIM, whether the source of the error is within the NIM itself or whether it's from something that the NIM is connected to, like the mobile data gateway. A limited full-screen operator interface that displays measurement counters and error messages, allows resets of these counters, provides a mechanism for reconfiguring the NIM, and allows the operator to print the log on demand. And lastly, some limited recovery capabilities. For example, under certain conditions, the NIM will restart itself and resynchronize with the mobile data gateway. Now let's look at the connectivity beyond the field trial, which is obviously of greater importance and significance. In the production phase, the NIM can bridge to, and will bridge to, appropriate attached network unique protocols such as SNA, X.25, TCP/IP. Multiple simultaneous sessions will be supported, as you've heard once or twice. Up to 16 sessions will be supported from the SU to multiple hosts or networks. For example, the IIN NIM shown here could support all 16 sessions that the SU could execute simultaneously, or they could be divided among several networks, and we'll see an example of that in just a second. Multiple sessions will give the end user the ability to execute several tasks at the same time, or to keep programs in the background of the PC to monitor unsolicited messages or input, such as electronic news bulletins or stock quotes. The NIM will be deployed in a redundant configuration as necessary to meet availability and performance capacity requirements. The production NIM will also contain some central office, perhaps switching-like type functions. A more extensive operator interface will be provided. More extensive error detection and automatic recovery capabilities will be required and implemented. The production NIM will be required to permit non-disruptive hardware and software upgrades. In addition, network management functions will be necessary, both to provide support back to the CD/PD network and also forward to the VAN. Now, obviously, these implementations will be VAN dependent, using, for example, in IIN's case, NetView facilities, but that will vary depending on what the VAN needs to implement. So network alerts will be handled for both directions. Billing requirements have not yet been determined for the production environment, but it will also be the NIM's responsibility to provide some appropriate measurements and data to the CD/PD and to the VAN for billing purposes. This example, as I said a moment ago, here's an example in the production environment, one where, in effect, there are 4 applications running on a PC equipped with the appropriate modem, and 4 sessions with host applications on different platforms and networks. Communication is through the MDG and the NIM to the value-added networks. In this example, customer application 1 or 2 might be attached to IIN. They could be email or an order entry application for support of a mobile worker. Application 3 on another network may be Dow Jones for monitoring stock quotes. Application 4 could be an information provider with data necessary for the completion of some immediate tasks, such as an insurance claims adjuster. The key point and the primary requirement of the CD/PD implementation is that the customer will not have to modify existing PC or the corresponding host applications in order to reach the mobile worker in this scenario. So, to simply recap and summarize, during the field trial, the NIM will bridge between the CD/PD network and IIN. It will use 3270 SNA applications for the field trial, and no software changes, again, will be necessary. Beyond the field trial, each VAN that is accessible from the CD/PD network will develop a unique NIM that addresses and corresponds to the specific network requirements of that VAN, the specific addressing, protocol conversion requirements, and so on. Again, no changes to customer applications or corresponding applications executing in the SU will be required. Up to 16 simultaneous sessions distributed among different networks and applications will be supported. The production NIM will support multiple protocols, in IIN's case, SNA, X.25, TCP/IP. They'll be deployed in a redundant configuration to meet availability and performance capacity requirements. They'll have fully functional, full-screen operator interface, contain functions for recovery, growth, retrofit, measurements and reporting, billing, alerts and alarms, error logging, and hence provide network management functions to both the CD/PD side and the value-added network. And that's the concept behind what we'll be implementing for the networking connections to the data services, as Kirk mentioned them. The last task here really is terrific. It's even better than VIX. Your next speaker is lunch, which is even better than a break. This may be the only and first opportunity I ever have to say to 1,100 people, let's do lunch. In any event, lunch will be served in all the hallways surrounding these rooms. It's a buffet lunch, and we are very much close to being on time, so we will resume again at 1:15. In the meantime, thank you.